mean, you can just write the notes when he's teaching and then just compile that separately. So it's not much to do. Use a separate bulb. Oh, for the bulb we can see. Good. You want to change to this. Good. I saw you taking notes. Why don't you tell them?
Am I audible? Okay. So let me first start by recapping what Suchetan essentially said quickly in the next couple of minutes. So the essential takeaways from yesterday's presentation was so the first lesson that we learned was that UV divergence seemed to be a very universal feature of entanglement entropy in generalized QFTs, primarily because of the reason that these are placed, these kind of theories we put on a kind of continuum, and there is no sort of cutoff. We have to smoothly take the cutoff to 0, which is the reason for the divergence. And what Suchetan tried to convince us was the fact that this is a property of the local algebra, which is precisely why we are looking at these objects. Okay, so with time, I mean monotonically with time, sometimes you will observe that the size of my letters going down. So in that case, please just let me know if there is any problem. People sitting in the back, if you have any problem in seeing or anything like that. The third thing that he discussed was the Rieschneider theorem, and just to reiterate again, I would like to properly state it, and the way it is stated is, so you choose a Cauchy slice in space time, and in that Cauchy slice you choose a open set. So this is a open set nu, which is part of a Cauchy slice, and you take this sort of pillbox like geometry which is extended. So this is the time direction, the vertical direction is the time direction. You choose a thin pillbox like structure, and this space is what he called u nu, and basically he constructed local operators which had support on u nu. So he constructed these smeared operators, something like this, and the essential statement was if you have another causal patch, another patch which is causally disconnected from it, so nu prime is space like separated, I should say actually. The statement was, if you start with the vacuum, then by applying arbitrary number of these smeared operators, you can produce your entire Hilbert space. So this actually is equal to H0. So here 0, by 0 I mean specifically the vacuum sector. So following this, So another way of stating the same statement is the fact that these smeared operator, when they act on the vacuum, gives a dense subset of your Hilbert space, essentially. And so the way, just to give a very quick sketch of the proof, so the way generally these kind of proofs that go into algebraic QFT structures are basically following the philosophy of reductio and absurdum, which is that you start with exactly the opposite statement. So you assume that these kind of operators, when they act on vacuum, they do not produce your full Hilbert space. So which means that there must exist, so there exists some chi such that chi where are the chalks? So and these points x1 to xn, they belong to this particular space-time region you knew. Then the statement was, if we start with this assumption, then with certain machinery in complex analysis, what he essentially showed us was that this says phi xn omega is equal to 0 for all points belonging to MD. By MD I mean Minkowski space in D dimension. So this means essentially chi is vanishing. But this contradicts with our starting assumption that we have started with a non-trivial state chi, which did not, which was not produced by acting the smearing operators on vacuum. So the immediate corollaries of these were no annihilation operator. This was a very short proof, as if you recall. It was basically it was based on the central idea that if I choose a operator from nu prime, or rather I should say u of nu prime, then phi of x, this string of operators, commutes with this a prime, which has been chosen from the algebra supported on the region u nu prime. And what we essentially saw was you can move around these operators, and essentially this tells you that a, this a prime which was chosen from u nu prime on this dense set gave you 0, which basically showed that you cannot have anything like that. Yes. Yeah, I'm going to come to that. So actually, okay, since we are already, since you brought up the topic of conserved charges, so yesterday there was a question that was asked by Chandramouli, which was this, so his question was, can a one particle state be a cyclic state? So of course he also defined cyclic and separating states. So again, to recall, a cyclic state is that state which if you hit on with all your elements of the algebra, you will get the full span of the Hilbert space. And separating was the statement that if a of omega is equal to 0, then the only choice that you have is a must be identically 0. If that is the case, then you call omega separating. Basically, you cannot annihilate the state. Now, to answer this question, whether a single particle state, so in general, when you hit on something like this, as I was saying, you produce the vacuum sector. So technically, the full Hilbert space consists of things like this. And these things are called superselection sectors. These objects are produced by non-local conserved charges. By that I mean, so for example, the example that you were talking about, gauge theories. So let us talk about gauge theories. In the case of gauge theories, so what exactly are these superselection sectors? So suppose if you're in a gauge theory, you are working with a particular state which has a certain charge. So whatever process you do upon this state, if you start with a state which had say 5 electrons, you cannot produce a state with 6 electrons or 10 electrons. So this charge has to be conserved, and this charge is essentially given by this kind of an object. This kind of an object, right, which is inherently non-local. So, okay, so there are various notions of non-locality that will arise in this subject. When I say, so this is what we mean by our conventional non-local charge. When you just write a theory which has a well-defined Lagrangian, etc. This is what I mean by non-local charge. And these indices that you see, these are precisely what parameterizes this Q. So if you start with the vacuum of a sector which does not have any charge, then you are only going to produce states here within this sector H naught. Now the point is that so how will you go to, you know, to a state which has, say, 3 electrons, 4 electrons, etc. Now the point is that there is this inherent thing, so that this your Hilbert space is dictated by your structure of your algebra, right? So until and unless there is some fermionic creation operator that is operating on it, so there will be two classes of operators in your theory, fermions and bosons. So there is no way possible that any bosonic operator acting on a cyclic state which is part of H naught can ever take you outside of H naught and produce something in H1 or H2 or any other superselection sector. It will always remain within that. Whereas if you hit on it with a fermionic operator, then of course there will be new particles that will be produced which will now change your charge. And those fermionic operators will contain this data. So in short, again, I have not thought very deeply about it, but the answer to Chandramouli's question is in some sense yes and no. Depends on how you are constructing your algebra. If your algebra, if you have included bosonic as well as fermionic operators, then you should not be writing your Hilbert space like this in the first place. It should be some, I mean, you should not think of it as a direct sum. Whereas if you don't have fermionic operators in your algebra, if you have solely bosonic operators, then this is fine. This is fine to write it this way. Yeah.
So what are these superselection sectors? Like you are talking about H naught, which you are calling the vacuum.
Yes.
So what does this vacuum sector consist of?
So see, this H naught comes with some index, right? So these contain states that will have zero charge. Okay. Similarly, H1, it will have charge of 1. I mean, however you want to parameterize it is up to you, but
Creation operators are also not part of.
sorry.
So, like I can have creation operators, like you said, like I can have fermionic creation.
Yes.
So those are not part of the algebra. Like
So if you decide that you are going to, so they can have support within your space-time region U of nu. If you decide that, okay, I am going to include those as part of my algebra, then you will produce all of these, starting from a vacuum which has no charge, right? Now suppose if you started with a vacuum which contains 7 electrons and you allowed no fermionic operator, only bosonic, there is no way you can produce, you can ever give me a state with 5 electrons, right?
why are you saying the state with 7 electrons?
Okay, the state with 7 electrons is the vacuum for this Hilbert space, right?
I'm just
So-
trying to understand. So
I mean, I should not say vacuum, I mean some cyclic state will be here present, which will produce all possible experiments that you can possibly do.
So, in that Hilbert space H7, there will only be a charge of 7e,
Yes,
no matter what you do.
yes. So this is restricted to within the superselection sector.
Are you being heuristic, or is this actually the case? So, you're taking E as the quantum.
Yeah.
So, is that how it's actually done?
I mean, if
So, H1, H2, H3. So,
yeah, I mean, how you are defining your charge, how you are quantizing it, it's up to you. You can like I just gave an example of electron because electron is a fermion and it's just easy to explain. But
these fields that you are defining,
I mean, think of it this way: these objects, these numbers that you see, these indices are related to these non-local charges, non-local conserved charges.
so each
So
HI has some corresponding Q.
exactly. So this data goes in here.
Yeah.
This Q data goes in here. Yes.
What are these fields? Like, can't I have from
Yes, yes. So see, you can have a fermionic theory where you can have this. So if you recall,
If acts on vacuum, shouldn't it produce a 1 electron state?
yes,
So then why?
but then you are out of your super selection sector. Suppose these were not part of your algebra. There are two possible cases. These are not part of your algebra. You are not considering these, right? I mean, you can choose to work with the theory with just the Lagrangian minus 1 by 4 f mu nu f mu nu, no size, right? What are you going to do then? And I have given you a state. You have started with such a Lagrangian, and I have given you a state which contains some number of charge particles. How are you going to go to a state with total charge something else, because charge has to be conserved?
Theorem
That's-
states that if you have, you take any algebra, I mean, take an open set U.
What theorem? Riesz
theorem.
Leader, yeah.
So you take any U
Yeah.
and consider the algebra of it, and then act on omega,
Yes.
and then you can get the vacuum sector.
Yeah, yeah. I mean, you should not say vacuum. Yeah, one of the super selection sectors. So you start with
Omega is for the vacuum sector, no?
yes. So that means each of these technically has their own vacuum.
Yeah, you could say that. Each of them has a cyclic vector.
Exactly. Each of them has a cyclic vector sitting in them.
So this argument that you gave, so I'm getting confused by this now. So what are you integrating over in this? So this is like you're considering some algebra again,
Yes.
and now you're saying that okay, if this kind of thing acts on omega, then it will produce a charge.
Yes.
And to me, it seems as if this is an operator in some A U.
Yes. Now this thing contains creation operators of fermions. These are not bosonic.
So, okay, inherently, it is assuming always that he's talking about bosonic.
Exactly. If you are within the bosonic sector, so this is the answer to Chandramouli's question. Can you have a one particle cyclic state? The answer is yes and no at the same point of time in some ways. This is my understanding. So I don't know if that made sense.
One particle can be a bosonic particle.
That's a yeah. I mean, I don't know.
Would that be part of the vacuum?
So it can be a bosonic particle, but then it has to have some kind of conserved charge associated to it, right?
So, can you go further on this? So, Chandrapali asked you whether it's can be a cyclic or not. Whether one particle.
Yes,
so
yes.
We are saying this is like some one particle state. If
So
it acts on omega.
exactly. So omega is a state with no particles. It acts on it. It produces one particle.
Okay.
Okay.
Why is it cyclic now? So
Why?
you're saying that whether it can. The question
So now your algebra contains fermions, right?
Okay.
Now there is no harm in you going from H1 to H2 to H3 to any number of charges that you can produce, right?
Okay, so now you act on any.
Yeah.
The algebra.
Yeah.
You can have charge scalars. Why are you considering fermions and charge?
I mean, this is just a specific example that I am picking out.
So then
I mean,
charge scalar, then
yeah.
your external scale will be bad.
For charge scalar, I have to think a bit more. But again, for charge scalar, I have to cook up some nice object like this. Yeah, some kind of charge operator that I have to cook up. So this is just a
Charges will separate your full input space into various supersections.
sorry.
So those.
Yeah, those charges will essentially do the same thing. Like I just need super selection sectors. So super selection sectors do not talk to each other, right? So once you have, yeah,
This thing also is valid in case when your vacuum is degenerated. Like in let's say for example in
Yeah.
time space you degenerate vacuum, right?
yes. So
We are also in some super selection sector, right?
yes. So
Unless your charges you can't go from one super selection sector
to another, yes. If I don't have, okay, I should not say fermions. Let me put it this way: charge creation operators. Is that now that will possibly answer your question. I have charge creation operators. Now whether it's a boson or a fermion doesn't matter. that I can have, right? Even with. Okay. So then we looked at von Neumann's theorem, which is the statement that, oh, sorry, I should, okay. Yes?
No, nothing.
Okay. So we define this object called a commutant, which is set of all operators which commutes with A. So this is a shorthand way of writing. A was my algebra which was supported in the region you knew, and von Neumann's theorem essentially states that A prime, that is commutant of the commutant, is the algebra itself. This is the central statement. And finally another corollary was, if A and A prime are commutants, then omega belongs to H is separating if and only if it's okay is separating in A if and only if omega is cyclic in A prime. So please note, this is a if and only if statement. Okay? So if in case if you have something like this, that A and A prime are commutants, then the role of basically then it will be separating in one of the sectors while it will be cyclic in the other, and vice versa. Okay. So moving on. So this is what roughly what we did last time. So now this is
This last statement.
sorry.
So if A and A prime are commutant, then only this is valid.
Yes, yes. So if A and A prime are not commutants, what we saw yesterday, if you recall, if omega is separating in H, then omega will be cyclic in A prime. This part was true. If the other side, that was not true. So if you want to prove the other side, in this case, you need a small result from linear algebra, which is basically that. So if you have K, which is a subspace of your Hilbert space, and if the operator K acts on K such that this is an invariant subspace, so it does not take any vector out of it, and if say, why are these chalks breaking off? So this object is the projection onto this subspace K, then what you can show is this is true. Okay. So using this result, you can show the other way, and this thing will only work if A and A prime are commutants.
Okay. That's true for the general vector, right? Not just the vacuum.
Sorry.
Is that true?
Yeah. So if omega need not necessarily be the vacuum. It has to be just separating in one, and so. Yeah, I mean the discussion that we had, we just discussed.
No, I mean the annihilation operator. There's no annihilation operator. There's 4 points that you've written.
Yeah.
So from yesterday's proof,
Yeah, I mean the way, just to recall, what happened was you choose some A within A prime.
This A was, I mean, the algebra observes on some set, right? On some open set U.
Yes, yes.
But now if I set U to be R3, 1,
You can't do that because there is a statement which follows this corollary, which precedes this corollary,
okay.
rather. And the statement is, you need to have an open subset nu such that there exists a non-zero complement nu prime
Okay.
such that this is equal to phi.
Why do you need this?
You need a non-empty nu prime. Then only this will work. Then only this holds. So,
You need this for that to hold.
yes.
But why do I need this?
What?
Why do I need this?
What? Why? I mean, they are space-like separated. They are disjoint. That's the statement.
Okay, maybe I'm not understanding. We can come back to this later.
Okay. I mean, you do not agree with this statement?
I agree with that statement as long as you are saying that there is no annihilation operator in any algebra of observables.
My point is, you cannot make this your full space-time. You need this nu to be such that the closure of nu should not be full space-time. That is the main point. Closure of nu should not be.
But why is that a requirement?
I mean, it is. I'm forgetting the argument, but it is required somewhere. I mean, I'm forgetting the argument at the moment, but there is something like this. I don't have a offhand answer. Okay.
You want to consider entanglement between regions, right? That's the motivation.
Right, I mean, but that is like some, later on I would say that some application, but when I write a general thing about like, general theorems in result, I would qualify that statement with saying that as long as.
So, and no annihilation operator means here that.
I mean, I can see one obvious reason. If your new closure is your full R1, 3, then you have no way to define smeared operators in A prime. I don't know how you are going to define smeared operators in A prime because you need a integral, right?
Correct,
But
it's a function that is valid, like Gaussian, for example. Gaussian is a smearing that's valid across the space, but it's two smearing function, right?
no, but the support has to be only restricted within nu prime. It must be, you cannot have tails.
No, but
So,
I'm saying that if U prime is my full space, my point is that why can't I
Gaussian is non-zero. It's not zero. It has a support.
yeah, but it has tail, and the tail, like, okay, when we say support, I mean a strict support. You cannot have a Gaussian has a infinite tail, right?
It's not dying, so it's non-zero. If it's non-zero, then it's okay.
No, I need. So when I'm writing this object, I want this to die outside the closure of nu.
Outside the closure of nu.
Yes, I want this to die.
Right.
A Gaussian is not going to give me that. It will always have tails.
That is true. But yeah, okay. So, you're trying to argue why nu prime.
Yeah.
Okay.
If you put a Gaussian here, you can't, right?
Right.
It has support everywhere.
That I agree with. I'm just saying that if U prime is full space time, Gaussian is a well-defined scaling function on the full space time.
Yes.
Yeah, that is true. But this is
I'm-
relevant here.
I'm talking about the other sect. So, okay, I think we are we can come back to this later. So, as I have said before, MD is what I'm going to denote Minkowski space in D dimension, and U and U prime are causal complements. And This one.
No, for separating to cyclic. Cyclic to
Separating to cyclic, we did the proof yesterday. I think the other way was.
we did from cyclic to separating, right?
Sorry, yeah. We did cyclic to separating. This way is.
Cyclic to
This, okay. I'll.
do you can just tell like some
Just a moment. I will. So one is of course. Yeah. He does says the IFF part.
it's in the first chapter, right?
I don't. Yeah, I mean, no, he does say. I mean, I can show it to you. He does say that, and he specifically also uses this particular statement. And another is. So these are one F.R. Jones notes. It's in his website. I think it's called Introduction to Von Neumann Algebra or something like that. Okay. Okay. Oh. So okay. By causal complement, U prime are basically it consists of all those points that are space-like separated from all the points in U. Okay. If that is the case, then Haack duality states that this is the central statement of Haack duality. Which is that the commutant, that all the operators that are commuting within your within your region of interest is essentially the algebra of the causal complement. That's the statement. Now, the immediate consequence of this is that if U and U tilde are two open sets, what you can prove is this is true for von Neumann algebras. Yes, only von Neumann algebras. By the way, there are certain very specific quantum field theories where this duality fails. Yes, it fails. They belong to type 3 von Neumann algebra, but it still fails. They are a bit exotic, but for most putative QFTs, this thing seems to work. Okay.
But doesn't this say A dash equal to A double dash equal to A?
No. This is not the statement A double dash equal to A. That's a purely algebraic statement.
This will imply that, no? If you and U dash are complements, put a dash on both sides.
No. This is okay. This is about the causal structure. That is about commutants. You don't need any causal structure or anything like that. I mean,
Put a dash. Then since U and U dash are complements, complement of a complement is just same thing.
U dash is the causal complement. This is a region of space-time, and it's the algebra associated with that space-time. This is not the same statement as von Neumann.
U double dash U.
No. You need not have U union.
What do you mean they are causal
Okay. Yeah. Of course. U union. It has to be one Cauchy slice.
U double dash is U.
U double dash is U. Yes.
So hence A double
Again.
dash with A double dash.
Okay. Okay. Fine. Yeah. Go on.
So then this implies A double dash equal to A, right?
Can you just write what he's saying?
What he's saying is.
This is true.
If
This
you
we
take
know.
the prime on the whole thing, the whole equation,
Yes.
right hand side is A double prime of U.
Yes.
The left hand side will be A prime of U prime.
Yes.
Now that using the same equation, you can rewrite it as A prime, A of U,
Yeah.
Saying A of U is A double prime of U.
Yeah, so this is if you can put the prime either on U or A. Okay. So you can just, so since U double dash is U, always, I thought A dash is always A double.
But the thing is that this thing is known to fail in certain cases. So, so my understanding was that this is a space-time statement.
Sorry. So when you define commutant, right?
Yeah.
The A prime that you define.
Yes.
So
No, it need not be. It need not be. It can be, yeah, it can be across all full space-time actually. In this case, it has to be. So that is why this is a bit very specific. So no spatial. I mean, it's a Cauchy slice. It's part of a Cauchy slice. Yeah. Okay. Sorry, I should have. These U and U prime are like space-like, and they are space-like separated, and so on. So yeah, this is the Cauchy slice. Sigma is the Cauchy.
So you mean U prime is the space-like portion on that Cauchy slice?
Yes.
Not outside.
Right. Okay. So so this is the statement of Haack duality, and okay, let me just continue here itself. Okay, so the now I'm going to define something called the Tomita operator. So we are now going to get ourselves accustomed with what is known as Tomita-Takesaki theory. And the definition of this operator is, so SI is an unbounded antilinear operator which acts on a state psi like this. Okay. Now, so okay. The first thing is that note. So okay, psi is cyclic. So because SI is an unbounded operator, you can only define it at best on dense sets, which is fine. But at the same point of time, since psi is separating, in case if so, okay, maybe I should. Yeah, right. Sorry. So the thing is, what we saw is that zero. So we can separate. Sorry. Oh, sorry. I have not finished it yet. Okay. Yeah, I should just write it here. This is the okay. Yeah. So you can think of omega, this psi has to be your vacuum. Now psi is cyclic and separating. Now the thing is that for separating, this is what we have. Now it might seem that there is an inherent contradiction, but we get around by the fact with the fact that SI is an unbounded operator. So what happens is, you see,
Why do you say this apparent contradiction?
so A, of course, we know that it cannot be an annihilation operator. It's clearly not zero. But you can create modes. So within a bounded space-time region, you cannot have modes of definite negative or positive frequencies, right? Because momentum eigenstates are not normalizable at all. And precisely because since we were talking about, modes always come associated with e to the power ikx, and we integrate when we break down into Fourier modes. So you need the full space-time region, right? But what you can do is you can write operators which are arbitrarily close or a very, very good approximation of annihilation operators. right? But on this side, if A is very close to annihilation operator, A dagger is very close to a creation operator. So on this side you have something very, very small, whereas on this side you have something very, very large. And this you can fine tune to be arbitrarily small. This can only be achieved if SI is unbounded, right? So, so this is a bit of a heuristic argument. By yeah, so by that I mean it is for all practical purposes. If you calculate the norm of this A of psi, it's something very small.
But states are anyway depend only up to norm.
Huh?
States are depend only up to norm.
Yeah.
So small norm statement is just a state with a very small.
Yes. No. Okay. So let me put it this way. So what is an unbounded operator? So this is something which Suchetan did define, but I am going to give you. So suppose there is some basis in which this operator X acts. Okay. Now I also say this state psi C and psi n. Okay. Now this object is finite, but when you calculate this object and you consider its norm, this thing blows up. This is the same thing. If you, well, when Suchetan defined it, he divided by the psi norm, modulo that. If the numerator diverges. So my point is that these Cn's that you see, they are arbitrarily going to 0. You can fine tune them. But this entire object, x of psi, sitting on this side, x being a hat and psi being psi, this object is something finite. This can only happen if these lambda n's are arbitrarily large, which is basically to say that these S psi's are unbounded operators. Okay?
So you just that A psi equals to 0 is just something that is reminding us what we did earlier, but A psi over there is just something very small.
Yes. I am just motivating why this is an unbounded operator. And this is the
unbounded.
Yeah.
Okay.
Which means this is not part of the one Neumann algebra. By by definition, one Neumann algebra was the set of all bounded linear operators, etc., etc.
A psi ka norm is small is the statement, right? Whatever psi, if psi
Yes,
is
yes,
norm is,
yes.
A psi is norm is
Yes.
small.
It's almost 0, right?
It can't be arbitrarily small.
It can be arbitrarily small, right?
It can't be, right? We proved A psi locally can't be arbitrarily small.
No, we proved it can't be exactly 0. I can make it arbitrarily small by acting it on with modes of very, very small energy, right? That I can do.
That's confusing, right? I thought we said we can't make A psi arbitrarily small is the statement of.
No, A psi cannot vanish.
Or not. What is exactly zero? It's
Huh?
arbitrarily small.
Sorry?
Exactly mean. Is this annihilation, man? Something annihilates the state, it's zero.
0. No,
Proof of the fact that when he said annihilation does not exist, what he said when he started with this assumes that A psi is 0, not A psi is
yeah.
really small.
I am not. It's not epsilon, some order epsilon thing.
There exists such a where it's exactly 0, then no.
This is the statement of separability. These are exact equalities. You have to think in terms of limiting processes here, basically, like the way we defined weak limits, etc.
But if A psi is arbitrarily small,
Yes,
then A psi
it's arbitrarily small but never reaching 0. That's how you should think of it. It does not annihilate. That is what it means.
if it's arbitrarily small, it means it converges to zero, right? And
You-
a state statement means it strongly
Where is the
converges to
sequence?
zero. What is the sequence?
There is,
that converges to zero?
yeah.
Because he's saying arbitrarily small.
What is the sequence? Give me the sequence that
He's
converges.
saying it's arbitrarily small.
What do you mean arbitrarily small? It's just a number. Give any number. Give any number, I can give you a smaller number. What is the problem?
No, doesn't that mean A psi is strongly converges to state 0. If you have there's no sequence. Where is the sequence which converges? A sequence is defined to converge or diverge. Where is the sequence?
All that I'm doing is I'm hitting it with mode.
There's a parameter which you can tune, which you can take as close as 0, and that's the sequence. With the tuning is the sequence.
Okay, so you define a sequence as the operators A in the algebra and
Because
A
AC
that
is
is on the
arbitrarily
side.
close to 0. So the A psi is a state which can be taken as of norm almost 0, right?
Yeah, so you could maybe then say that the limiting point A,
Sure.
A limit,
Yeah.
which will exactly
Arbitrarily
annihilate.
close to 0. So A psi can norm is arbitrarily close to 0, and hence its overlap with any state will be arbitrarily close to 0. And you can write the sequence.
Yeah, now you define the sequence. Now in the last, that limiting point of the sequence does not belong to the set.
Which set?
The set that you have, this
Yeah.
KU.
Your limit points can be outside the set, right?
I thought we have a closed algebra of A hats. No. A hats closed, right? Any
Yes.
sequence you write will converge within the set. There's a weak closure.
The weak closure, yes.
Or are you saying there's no strong closure? Is that what you're saying?
No, I'm not saying there do exist strong closures, but here, I mean, you should not think there is some sequence or anything like that. All I'm saying is there can be operators with extremely by which I can produce modes of extremely small frequencies. That's how you should think of it. And this particular frequency, I mean this is a very heuristic argument. This is not something which I'm claiming to be mathematically very rigorous.
No, I guess the confusion is I was thinking of some strong closure and the statement is there's only a weak closure.
Yeah. Yes, you can say that this is a statement of closure in that sense. Okay, so indeed this thing is also we will now define in fact closure of S of psi, and that will be defined under what is known as the weak limit, which is then we say that S psi of x is equal to y. So these points also you include within the states on which your SI acts, and this is how you say that. Okay, so there is the one catch that this entire thing is going to make sense only if, in case if this goes to 0, I better have this also equal to 0. The reason being, if you consider this object where A prime is something that belongs to A u prime, if you consider this object, then what you can show is now if you consider the complex conjugate of this object, which I am writing as C bar, so my complex conjugation will be written as bar, what you can show is, and all that you need to reach this result is the fact that A prime and ANs commute. But if that is the case, because now AN size in this weak limit vanishes, this object also has to vanish, right? So this object has to go to 0. So C is this object. Yes. If this is the case, then this better be true. The reason is you consider this operator where A prime I have chosen from the commutant, and this is C, right? The complex conjugate of it is given by this. This object is non-zero by our assumption. I started with the assumption that say this is y which is not equal to 0. So this object is not equal to 0. This object, because of this, is equal to 0. But this is nothing but the complex conjugate of this. So clearly there is a contradiction. So henceforth y has to be 0. Okay? Is the argument.
Just a second.
Hmm?
I couldn't follow. Let me see. Just give some time.
Okay, I mean you can.
So the basic underline is that if the sequence goes to 0, this will not be 0. The A dagger, the sequence.
It has to be 0. I started with the so most of these proof will work with. I will start with the opposite thing. Suppose it is not 0. Then I just showed that if this is not 0, then you end up with a contradiction. So henceforth it has to vanish. That is the logic. Okay? All that I am doing is these are the limit the limit points. When you take these sequences, you include these limit points under your action of S of psi. That's it. Okay.
Sorry, what is the point of this? What are you trying to say? So x and y. So I see that S psi acting on x is y. That's fine.
Yeah.
So if it is so, then this is closable. Okay.
Yeah. I just defined closure.
Okay.
Yeah. That's it. This is just part of the definition.
Then it means the limit. So you're now saying x is 0, right? The x that is.
Yeah. In case if x is 0, then I better have this also 0. That's the statement.
Okay.
So you have to be a bit careful when you are that's
Okay. So that's what you are.
yeah. Huh? I just considered this object, this number. I mean, I use this so that I can move around and I can. I mean, I use the commutation A prime and A commutes. So that's just. This object is non-zero, right? Oh, okay. So, okay, maybe this is a thing of. Yeah, I should explain this notation. So, if I have states psi and chi, in standard quantum mechanics, you would write this as this. That's it. I will be using this kind of notation. Okay? So, the left action of some operator, I am going to just take a dagger and put it here. That's how I am going to represent. So that it sort of looks like an inner product between two kets. That's that. Okay?
So just to understand, like what you are essentially proving is if you represent A ends with some sequence of matrices, let's say,
Yes.
and the eigenvalues of these matrices are progressively getting smaller and eventually tending to 0 for this vector. So you mean to say then that the dagger of these operators will also, their eigenvalues will also go to 0, right?
Yes.
Because dagger is just transpose and conjugate.
Right.
Okay, fine.
I mean, even if you multiply 0 with infinity, you get 0.
Yeah.
That SI is unbounded.
Yes,
but
yes.
This vector itself is.
Yeah.
0.
This is one way also of seeing it. Yeah. Yes.
And from that we conclude it like from any open set we can generate the full waveform.
Yes.
So now today this commutator operators are unbounded operators.
Yes.
So what you are doing?
You will see what we are going to do with Tomita operators. So,
And also one final thing, like so Tomita operator essentially took Q, converted an operator which has very small eigenvalues
Right.
to an operator which has very large eigenvalues.
Hmm.
Hence, it must be something.
It must be something. Yeah, basically that's the argument. Yeah. What? No, I mean, all my, see, my Hilbert space still contains a cyclic state. I still have my algebra of observables. I can still generate the full Hilbert space. This is just a special operator I defined. I defined how it acts on this dense set. That's all I defined.
But those operators are bounded operators and
Yeah, SI acts on only bounded operators because by construction our Hilbert space, the way we set it up was precisely, A of psi, all of these things will be bounded operators. They are part of the von Neumann algebra, and von Neumann algebra by definition has to have linear bounded operators.
More like a psi is a
just
state.
different thing from that.
Yes, this is something. Okay.
One can't define it as on the level of operators which can. So you need a cyclic separating state.
I need.
You mentioned this. So a psi.
Yeah.
It right. A psi forms a dense set.
Yes.
And we are hoping that okay, this dense set doesn't have any vector which make the S size norm, S psi is norm.
Yes, exactly. Not one, but okay, something. Sorry. No, that was action of S psi on something. I am just here. That's different. Yeah, my statement that something very small is going to. That's when you act S psi on it. This is I have not acted S. Okay. So what we see is from our very definition, Si square is identity. So I am just going to now list down certain properties of this operator. Si acting on psi will give you psi. It's simple to see. Both of them are very simple to see. For the second one, you just put A equal to identity. You get it. So the important point to note here is that Si is not Hermitian and also Si is not a projection operator. Now, like we have defined Si which acted on algebra, which acted on states which were produced by algebra of observables in the region A, you can have Si prime, which is the Tomita operator associated to the commutant. Okay, and what one can show is that Si dagger is equal to Si prime. This is a very simple exercise. All you have to do is show that this relationship is true. Just sandwich it between two arbitrary states lambda and chi and show that this works using these results and the definition. Yes. Yes, I am coming to that. So yes, S psi is an antilinear operator. So what I have defined here is the adjoint of it. How am I going to define this S of S dagger? That is what I am going to do now. So because S psi is an antilinear operator, the
so the subscript is, I mean, is it to indicate that for different states you will have different S size?
yes, so I have chosen a particular cyclic and separating state,
Okay.
and this is acting on this. So this is my.
So it's like
So let me actually write here.
so psi is essentially denoting some like vacuum state.
Yes, I should say they are denoting Riechlider states. You should, I mean, now that we know that there can be, vacuum is not the only state that can be cyclic and separating. Now that you know that,
Even okay.
you can have S psi associated with each of those states in your Hilbert space.
Yes, just for my clarification, in the morning you talked about various super selection sectors.
Yes.
So is cyclic and separating state unique in one particular super selection sector?
No, you can have, no.
So that means even in let's say vacuum super selection sector, so there if there are many such cyclic and separating states,
Yes.
for each of them you will have different definitions for the operator which essentially implements adjoint, right?
Sorry, I didn't understand your question.
Oh yeah, so suppose there are two cyclic and separating or
Yeah.
n number of cyclic and separating.
Yeah. Actually, I will work out an example of finite dimension where you will see that you can have, I mean, the most generic state will be cyclic and separating.
Okay.
I mean, by creating a double copy of a finite dimensional system, if you use this mid decomposition and if you write the most generic state that you can think of, you will see that it will turn out to be cyclic and separating.
Okay.
So.
So, I mean, I guess I understood, but I wanted to ask the same thing. That, so, basically, you're saying that there can be, so say there are no charges, it's just the vacuum sector, which is the Hilbert space.
Yes.
Omega is not the unique cyclic and separating state.
No,
Okay.
it's not. I mean, there can be more cyclic.
How will you be able to generate more others given omega?
Okay, there is no prescription like given a cyclic state how I can find others.
Okay. Maybe some.
This is huh?
I thought maybe some multiplication with some operator would get.
I don't know of any prescription from which given a cyclic state you can. But
I mean,
you can possibly what you can do is what one possible way would be going to the right basis, and if you have found out one, you would try to fiddle around with the coefficients and try to figure out if that would be the most naive thing to do, right? Because all these things are finally determined by how this object is acting on your basis. So if that is fine, it should be. Okay. So for antilinear operators, adjoint is defined as so this is the definition. In conventional quantum mechanics, what you would have done is you would have put a star here, right? Or rather there would be a bar here because that's what I'm, right? But this is how you are defining adjoint for this class of operators, okay?
So if I remember correctly, there's a distinction between what is self-adjoint and what is Hermitian or something, right? Can you take the fitting a bit more? I forgot what exactly the distinction is.
Yes.
About boundedness.
Yeah. So for antilinear operators, if you so
Like for example, what I'm saying is when you say SI is not Hermitian, that in that third star.
yes,
Third star.
yes,
So
Okay, I will tell you this. If W was Hermitian, this is how you would have defined hermiticity. Okay? Now notice the difference here. It's the same expression, but now you are not taking a complex conjugate.
Antilinear part I understand.
This is about antilinearity or linearity.
Yeah.
I'm asking
Hermitian,
Hermitian.
if the operator is bounded
Ah.
and self-adjoint, then it's Hermitian.
Okay. If it's unbounded and
Then there are multiple cases. If it's unbounded, then multiple things can happen.
I see. So the
Yeah.
fact that it's not Hermitian.
So
is-
there are three things: Hermitian, symmetric, and self-adjoint.
Yeah.
Okay.
So self-adjoint is the last thing.
I see. Okay.
I would say
When the domains of adjoint and A both match, then it's self-adjoint.
Okay. So the fact that here SI is not Hermitian simply follows from SI not being bounded.
this is, yeah, exactly. I think it is the unboundedness which creates this. Yes.
Yeah, that's also good.
Yeah.
It might not even be self-adjoint.
That's what I want. So is it? Yeah.
Yeah,
At this
it
point,
might be.
SI could be self-adjoint but not Hermitian. That's
Yes,
what I'm
yes,
about.
yes.
So there you can't have the second part there, right? That notation doesn't work for non-Hermitian matrices, right?
What?
Then you wrote chi line W diagonal
Yeah.
line.
Yes. Yeah. Sorry. This is how it will work. So there is something in linear algebra called the polar decomposition, which basically sorry. Okay. So there is something called a polar decomposition, and what one can do is where this object is anti-unitary and this matrix is Hermitian positive definite. And the thing is that this decomposition is unique. So this is a result that I am going to use from linear algebra, that given a operator like this, you can always decompose it in this way. Okay. What immediately comes out of this is that, okay, so this object delta, this is known as the modular operator, and J psi is known as modular conjugation. Okay. What immediately follows, again, I'm going to just quickly list down certain properties. So this is point 1. This is also true, and for any smooth function, so these are the three properties that the last one actually follows from this. F is any smooth function, because when delta psi hits on this, since the eigenvalue is just 1, so any function when you hit on it, it's simply f of 1. Okay. Okay. Another thing that comes out is, because S psi square is 1, this is identity. From here, what we can derive is this equality. But note that this object can also be written in this form. So both are the same statements, but what has happened is, look at this operator, delta psi to the power minus half. This is a Hermitian positive definite object. Hermitian positive definite objects can be written as some unitary matrix times some Hermitian object. Now this object is again positive definite. If you calculate the determinant, it's fine. If J is anti-unitary, then J square is unitary. But what happens here is, there is also this other decomposition that you can trivially do, right? But it says, the theorem of polar decomposition says that this has to be unique. But right now, we have two different polar decompositions, which cannot be. So the only choice that we have is J psi square has to be identity, and this object, J psi inverse, so this is 1, this is 2. So these are the two statements that follows. Okay. Now,
So
the first.
okay,
from here, from the left itself, like, so you have a
from here.
position of the
So I have done a polar decomposition. Up to here is fine. The claim is that this way of writing SI is unique. Okay? If I have given you a SI, you can write it in terms of anti-unitary times a Hermitian positive definite object. Now these are certain things that you can derive very easily. Again, using this particular.
J and delta compute. It can be on either side.
Yeah. J. I mean, I have not shown it yet, but yeah.
I'm just saying there would be a polar decomposition of that kind also, right? If it doesn't.
J and
Delta. Like, can I write SI as J delta or delta J?
no, not delta J, J delta.
They do not commute.
Yeah. So these are certain properties that you can derive. Oh, sorry. Yeah.
I'm just confirming because that also seemed like a good enough polar decomposition.
Yeah.
yeah, you're going. I mean, I just wanted to understand what you were saying.
Okay. So I mean these are just properties that follows from the definition. Now, if you consider this SI square is equal to identity, so this is just, I mean, SI square written twice, and I have taken the delta to the other side. Now, notice that delta psi to the power minus half I can write this way. This is a Hermitian object. This I can write as unitary times Hermitian. Note this is also positive definite Hermitian, and times something which is unitary. If J psi is anti-unitary, J square is unitary. Okay? So this violates the uniqueness condition, right?
How does it violate the uniqueness condition?
I have given two different polar decompositions,
For S square.
right?
S square, indeed.
For S square, right?
And
For this object, del psi to the power minus half.
Oh,
For this object, this is equal to this. This is one polar decomposition. This is one polar decomposition. So the only thing is, the unitary parts must be equal. The Hermitian positive definite parts must be equal, and that is what I have written. J square must be this. This part must be this.
But in the polar decomposition, the first matrix is anti-unitary.
Sorry.
The first matrix is anti-unitary. Here also is unitary.
This object, yeah, there is a polar decomposition theorem for unit, for Hermitian also. For Hermitian, you can write it as unitary times Hermitian. Yeah.
Are you defining S square psi as 1?
I am not defining this. This follows from the definition. No, this follows from. I mean, I defined it this way, right? This was my definition. A dagger psi, right? Now act on. So this is S square. I will act here with S psi. This is nothing but A of psi. So S square is identity, right? So that is what I have used, and then I have replaced with the polar decomposition, and this is what I have got.
I'm always skeptic when it comes to taking square root of the operator. That might sound silly to you, but that
you do not, okay, if you don't like, I mean, this is just a way of representing the polar decomposition theorem simply states that this has to be anti-unitary and this has to be Hermitian. This half is a conventional thing. I could have just written it as just delta psi. But in that case, all my subsequent calculations I will get, for example, here I will get delta psi square and things like that.
Positive definite taking square root.
Square root should be fine, yeah.
Yeah.
It is Hermitian positive definite, so. Yeah. Okay. This one.
No, the one you just behind this board. Writing down.
Oh, okay. I see. Fine.
This uniqueness is up to some complex numbers, right? That's not a problem.
I mean, up to a phase, of course. That's no, actually not even a phase, because there is a unitary operator that is sitting there, right? So it is exact actually. There is no ambiguity. Okay. Now for the commutant we had a but so this is what we have. This follows from the fact that S prime is equal to S dagger. And again, what this tells you, uniqueness of polar decomposition tells you psi and delta psi prime, delta psi inverse. So these are the two statements. Okay. Finally, the antilinear property tells us so this has to be true. So f bar means you take the complex conjugate. This has to be true for all smooth complex functions. Okay. So to be more specific, if you consider fx to be x to the power is, is this.
This delta psi inverse is also bounded, and delta psi was bounded.
Sorry?
Delta psi itself was bounded or something, was it?
No, you see, delta psi is precisely the Hermitian positive definite part. This cannot be bounded, right? Because this is anti-unitary. So here in this case, anti-unitary operators will always have bounded. I mean, it's always e to the power some complex thing, right? So whereas this thing is, well, so think, huh? Delta psi is not bounded. So this is precisely, you think of this as the phase part and this as the radial part. So if this operator is unbounded, this cannot be the. So yeah, in fact, the thing that is, so you can also see the other way of polar. Akhil, your question. Yeah. So the other way also, the other polar decomposition, you could have written this because here you see the commutativity come out, right? J psi square is 1. I'm going to act on J, right? So, I mean, forget S can be 0. S is any real. Sorry, not 0. Yeah, whatever. I mean, I can choose fx to be simply x, and then I can do this, right? Yeah. So the other way of writing the polar decomposition also is fine. Yeah.
So S cannot be complex. I mean,
No. S is real. S is real.
for all modulars.
Yes. This entire equation, this is real.
How did you arrive at this equation? J psi f j is f bar?
This is definition. This is of a anti-unitary operator.
Okay.
This is how anti-unitaries work. I mean, in general.
All right. Okay, that's what you've done.
Yeah, I mean, this is basically the operator version. I've done a conjugation. If f was a, I mean, in function space, this is how it's going.
But there are inverses here. So is delta psi and delta psi inverse. Is that correct?
Yes, this is delta psi prime. This is the modular operator associated with the commutant.
Okay.
This must be equal to the inverse of the modular operator associated with your original algebra A. Okay?
Fine.
This is inverse. Okay, now in very analogous spirit, you can define something called the relative modular operator.
Sorry.
Yeah.
How did the second equation from the top, like the second equality, the first equation? You use S prime as S dagger, is it? And
Yes.
How did it come?
So. Yeah, you have to use these things here. Just let me think. So. Huh? J psi square is 1. Yeah. Yeah, I mean, it will come from one of these equations. It's just difficult to sort of see through. You have to take the dagger the right way.
It's not obvious. Okay, fine. It will work out, but it's just, okay. I thought it was something obvious.
No, not very obvious. I mean, you have to basically stare at these three equations, and it will follow.
What about that equation?
Yeah. Yeah.
Debangshu, what about that one? S dagger psi equal to S?
Yeah, that is what we are using.
Yeah.
We are just constructing. Is equal to stagger. If I multiply here with A. Okay, I have to think a bit more, but it should come from, oh, I think it possibly, yeah. You multiply here with j psi. So from here what you have is j psi delta psi to the power minus half is equal to this object. Now, this, sorry,
That's dagger.
and this is nothing but dagger, this object, because j psi is anti-unitary. So when you take the dagger, you have to compensate one more complex conjugation, and delta psi is this is from this one. So you multiply both sides with j psi, and that's what you get using this. Is that fine?
I think so.
Yeah.
If you take S prime, then that's S.
Yeah, I mean, okay, just to show explicitly, take this equation, multiply both sides.
Yeah. Up to daggers it seems it's correct. I don't see where the daggers went. So AB dagger is B dagger A dagger.
This is on the left side.
Oh, sorry. J psi I have acted on the left. Okay. Now this object is SI dagger. This was Hermitian. This was already Hermitian, so no need to worry. This was anti-unitary. So to compensate, you have to take one more dagger. So it's not just right. So it's J double dagger, so which is again J, and henceforth this. But this is nothing but equal to SI prime, which is that. Okay. Okay. So, Ovik, how long can I go on for? Huh? I'll try to stop by 12:30. Huh? Yeah.
Delta power half J psi is SI dagger.
Yes. Yeah. I mean, it's because of the property of. Huh?
When you say J will go through the delta something like that.
Yeah. I mean, they will commute.
They won't know. I mean, if you put J on the left it is S, on the right it is dagger.
No. J psi is it's a anti-unitary. So the dagger is not exactly the way it should work. I mean, you have to take one more complex conjugation for anti-unitaries. This is how you. I mean.
Confirming J delta half is not same as delta power half J. Right?
I mean, from here we don't see that.
This thing, I thought
Yeah.
you were arguing that you said J will go through delta or something. I thought you said.
Yes, this is what it shows, right? It does go through. I mean, you take.
I think it won't because apparently when it went through to the right side, it became S dagger.
Oh. Okay, so okay. All that means is this is not from where it will follow probably. Yeah, this is not where it will follow from.
So his question is whether they commute or not.
Yeah. No, they commute. That is,
J and
yeah.
delta probably won't commute. Maybe that manipulation you did is fine. Like I'm just saying J and delta 92 should commute.
And then I don't see.
Yeah. So this is from another.
Okay, this is okay. What I should say is that okay. This should commute when S belongs to R. This is something very specific because this follows from this condition. You see on the right hand side I have taken a F star. If this would have commuted, I should have written here F of simply, not F bar, but simply F of. That would have implied that this is commuting, right?
Isn't that the minus sign coming from the inverse and the I will also, taking the complex conjugate, the I will go to minus I, that's why it is.
Yeah, that is precisely why. I mean, this from, yeah, that is clear. I mean, our entire point of discussion is whether this also implies commutation between J and delta psi. That is what. Okay, I don't have.
Delta psi is Hermitian, right?
Yeah.
Delta psi half is not Hermitian.
No, it will be, right?
It will be.
Yeah. If that is Hermitian, of course.
It could be that delta psi dagger is minus delta psi.
No. That's a positive Hermitian, positive definite Hermitian
Half,
operator.
delta psi for half. If you take dagger, it could be minus delta psi dagger.
No,
Delta
that's
will have
I mean-
eigenvalue matrix has only positive
Yeah.
positive numbers.
But half.
So f of, so you take the power, diagonal matrix takes the power, and everything gets square root. So everything is positive.
yeah. This is then probably not where this thing. Probably this argument is wrong.
You're saying this is true because you have got this relation. Are you sure about this relation? J psi delta. J
Yes. This I'm pretty sure of.
No, the last line.
Yes. We are going to use this in fact extensively.
So from this, okay. So you multiply J psi inverse on both sides. What do you do to show that it's actually commuting? So, right, identity. So this is true.
This is true.
So commutation with half is different than it commutes with delta.
Yes. I mean, what is crucial is this power is complex because this follows from this kind of a relation, right? Where you have the liberty to take.
No, it doesn't even commute with delta. Right. So
This bar is precisely what is making sure that this thing is delta to the power plus is and not minus, right?
So this relation is only for S purely real.
Yes, this is only for S purely real. So yeah, to answer Anisha's question, I have to think more, but this is probably not how it can work. Okay, now we have something called this relative modular operator, which works in a very similar fashion except some changes. So this is how we define it. So there is some notational thing that I should point out. In maths textbook, this is reversed.
phi is also
So,
cyclic separating.
huh?
Phi is also cyclic separating.
No, phi can be any state. Phi need not be cyclic separating. Okay. However, what we do assume is this is true. Okay. So just simplify. Psi is still cyclic separating. Here also, phi can be any state. Okay, in this definition also it is cyclic and separating. Okay. Following this definition, some of the properties that follows. This is identity. So this is essentially, if phi was equal to psi, this is essentially the statement S of psi square is equal to identity. That is where it would have boiled down to. And also you have, again, very analogously,
I thought that you needed, so when you write before the relative modular operator,
yes,
right, you define this S of psi, the usual whatever Kamita operator.
yes.
So that psi necessarily had to be cyclic and separating
Yes.
to be able to define that.
Yes.
Now what you're doing is that I take that operator, I just call it S psi vertical psi, the earlier operator that I defined.
No, this is phi.
No, I'm saying if that was like say psi,
Yeah,
the
yeah.
notation will be S psi vertical psi. Right? Yes.
Yes.
Now if I think of the S phi psi,
Huh.
right? I mean I could change my psi to be phi. I would have a state. I mean, I would need. I can only define that if f of phi is if phi is cyclic and
Okay.
right?
In this equation.
Yes.
Yeah, for this specific equation, yes.
No, but I'm saying that I don't think that you can define, like somehow it seems like I'll run into trouble if I allow phi to be not cyclic and
No. This is if phi is also all these, okay. These two statements are true if, Anish, these two statements are true under this condition. So this is a still, this is a, this object is a well-defined operator. I mean, these two statements are true under this. Okay. So whenever I am writing something like S phi psi, of course I mean there is this inherent thing where I mean that this has to be true. But in this definition, this can be any state. Let me be again very clear about this. Okay.
So this guy won't have a dagger.
This guy won't have a natural dagger. Yes. Okay. So now, forget that again phi is cyclic. Now phi can be anything. This is my definition of relative modular operator. Okay? Both are psi phi. Okay? The first, let me just write down some properties. What you can show is that this is positive semi-definite. For phi equals to psi. Yes. And exactly like before, we also have a modular decomposition here, which now we just put the words relative in front of it. This is relative modular conjugation, this is relative modular operator. Okay? Now, okay. So, one thing that is one has to be a bit careful when they come to this particular this thing. Recall that phi is not necessarily separating. So it is possible that this object phi psi, which by inherently is a non-trivial operator, it has a non-trivial kernel. But if that is the case, if S psi phi does have a non-trivial kernel, it would also mean that it is also the kernel for deltas, right? So this will produce an ambiguity in defining this object in this polar decomposition, because what you can always do is, so if there is this kernel, yeah.
Why did you start saying that it has a non-trivial kernel? What was the argument for it?
Because phi is not necessarily separating. If something is not separating, that means there is some non-trivial operator A within your algebra such that A acting on that algebra indeed gives you 0, right? So it can have a kernel. I mean, it's a possibility. It may not have also, but if there is a kernel of that object S, it will also kill off. I mean, there will be a bunch of vectors when you act this because of this particular relation. When you act it with delta, it will go to 0, right? But now, yes.
Can you explain the argument why it has a non-trivial kernel in this equation? So you're saying
The argument is just that
psi is still cyclic
cyclic and separating.
Psi is still cyclic separating. Phi can be any state. It need not be separating. And what is the definition of separating? Separating means if A acting on phi.
So we still have some algebra AU with respect to which this is associated, right?
Yeah. So because phi is now not separating, if this is equal to 0, it does not necessarily mean that A will be 0.
Fine, but A dagger is acting on psi. Fine, sorry.
This is a definition. Yeah.
A dagger is just something. You could call it A dagger itself.
Yeah.
Okay. Right. So A dagger could annihilate phi.
Yes. Because it's not separating.
Right.
And this will be non-trivial. It need not be necessarily 0.
It may not be non-trivial. Right.
Okay. Is the argument clear? Okay. If this is the case, then you see what you can always do is within this decomposition, you instead of writing down this object, so suppose this kernel, go to the kernel subspace, you will find some basis. So kernel of S phi psi. So set of all these vectors, psi n is your basis. What you can do is you can always add this kind of an object to your delta. But you see, this entire object is also still Hermitian now. And if I mean, because
What is capital X?
this is not capital X. Okay. Sorry.
Okay.
Yeah, I mean this object will come multiple times. So it's not capital X. It's this. So what you want is you want a unique polar decomposition, right? Now this part is fine. Now if I would have acted with elements of this kernel, this part will give me 0. This part need not necessarily vanish. So how am I going to make it unique? I am going to demand that this object J psi phi annihilates psi n. So J phi is this psi phi annihilates all elements in the basis, which means it annihilates the full kernel. Okay? What?
J is an anti-unitary operator.
Yeah.
And it can annihilate stuff.
Yes. I mean,
Unity operators don't annihilate anything.
no. This.
They can.
Yes. I mean, I can. This object does not have any matrix representation. Firstly,
J
right?
has some inverse, right? J is equal to
Yes.
1.
This can. I mean, I am defining it that way. This I can always. This I can always do.
Okay, I see this point.
So there is this inherent ambiguity where I can add a bunch of Hermitian stuff to it, and all these relations will remain unchanged if I consider this as my delta tilde half, right? So now in order to make sure that this operator is indeed equal to this, the only way around is I have to make sure that this object kills every element in this. That's the argument.
I think you understood this point, and I don't understand either. That eigenvalues of unitary matrix are always on the unit circle, right? So
Yeah. These okay.
If U acts on a state psi and then gives you 0, that's as if U has an eigenvalue 0.
Yes.
So that operator cannot be unitary in that case. So such a thing doesn't hold for anti-unitary, is it?
No. Okay. So these are not eigenvectors of this object.
Doesn't matter. If it kills it, if
Yeah.
J psi
Yes.
is 0,
Yes.
that means it's eigenvector with eigenvalue 0.
Yeah. Fine.
Then that means that it cannot be unitary and anti-unitary also probably.
Even
If I check
No.
the definition.
So
J square equal to 1 condition also. So I'm just confused.
What?
J square is 1, right?
If it
Yeah.
annihilates on something, then that condition is not valid.
J dagger J identity.
it should be. Now it's actually not.
So this you cannot have S square equal to 1
Where?
If you act on S,
No, a square equal to 1 is essentially this statement, and here also j square is not 1.
here also J square is not 1.
J square is not 1, by the way. Okay?
I think I'm just taking
No.
yeah.
This, you see, I mean, when phi is equal to psi, this is when that will boil down to, I mean, a square equal to identity, right? So even here also, you need phi equal to psi to go back to that. So in which case phi will also become cyclic. But here in this case now phi is not cyclic. Okay?
What is logic here? So you started with S psi phi is J psi phi delta half.
Yeah.
And now this has a kernel.
Yes.
And now
This.
this is unique at this point, right?
Yes.
Then why are you adding this additional thing? Now it's obviously not anymore. I mean, now you are removing the kernel. If
I am,
do this.
yes, I am in some sense what I am doing is I am going there, I am taking all the sort of the matrix representations of this kernel and adding it to this.
Yes, so this will give me some new operator. Let's call it S.
Let's call this object delta tilde.
So this J psi delta tilde will give me S tilde. Why do I want it to be?
No. It has to give you the same S, because this is still, look, this is Hermitian, this is an anti-unitary. This is still polar decomposition, and polar decomposition better be unique. You cannot have two different polar decompositions.
Like instead of delta to the half.
Right?
I mean, only if it is S, then I understand that it has to be unique. But why should this be equal to S?
What should we?
If you say that
Okay,
this
sorry,
is
I should.
equal to S, then I understand polar decomposition is unique. But this is not. Oh.
I mean, this I can also.
Like adding and subtracting.
Yeah. I'm adding and subtracting. Right? This I can still do. This is equal to my this delta.
Okay, so
Right.
Can I just
Yeah.
polar decomposition of non-invertible operators are or matrices are unique?
Yes. So you also need. It has to be. So at some point, I don't think I mentioned this. S of psi phi has to be invertible. This object has to be invertible also.
So psi phi has to be invertible.
Yes.
But it has a kernel.
Sorry. In just a moment. If this has a sorry, it has to be invertible only in when phi is cyclic. Yes, sorry.
Okay.
Yeah. Only phi is cyclic, then it has to be invertible. Now phi, I am specifically taking a state which is not cyclic. Yeah, that's the statement. Yes, right. Yeah.
I still not clear to me why that last equation is the same as S. Only if you can show that this is same as S, then I understand polar decomposition is unique.
Are you demanding uniqueness of polar decomposition to say that J psi on that thing will be 0?
Yes. I am demanding uniqueness of polar decomposition to make the claim that this object will annihilate the kernel.
No, but if you say that this is S psi,
Right.
given S psi has a unique polar decomposition, then it has to annihilate. But I don't even see why this is S psi. That is not at all clear to me.
See,
S psi comma phi, yeah.
I can always extract out this object, right? This Hermitian object out of it, right?
I mean, like, but what is it? I mean, I can always write +1 -1 there also. I mean, I will not say J psi acts on 1 and says gives me 0.
Debangshu, what? Okay, given that S psi phi has a non-trivial kernel, what then? What is the point?
So the point is, if this has a non-trivial kernel, I am going to demand that these objects J psi phi must identically annihilate them. J psi phi acting on elements of that kernel must be 0.
Then what happens?
Hmm?
What happens? If it can annihilate?
If it annihilates, then I have a unique decomposition.
No, but you just said no. It was unique for
See,
SI can be split as both delta and delta tilde, right?
comes from J square. No, but that's what he's trying to argue. No, but he's to show that S as a kernel, he's saying that
I think if I decode the argument like this, right, that you want delta to be positive definite, and the kernel of S really comes from the J factor.
right.
That's what he wants.
So yeah,
to show that S as a
So
kernel.
that statement uniqueness was for
normal SI, right?
yes, yes,
Now you're describing relative modular operator.
right.
So here, is it also once again true that this the polar decomposition of this will be unique?
Yes, yes, yeah, yeah.
Okay.
The polar decomposition is always this is a, yeah,
Okay.
yeah. The uniqueness is always true,
Yeah. So given that it has non-trivial kernel,
right?
so does it imply that you will be able to write that thing, that delta half? You can split it like that. Does it imply that?
That is what I am.
But you're saying JSI annihilates psi and psi, right? Psi and psi. Now it's no more unique, no? Both for your Hermitian operator, you could choose both delta half and delta tilde half. How is that unique?
No, I mean that is what I mean. We were this I put later actually. I did not. I mean this is what I was calling my new delta tilde. This is what I was calling delta tilde, and it seems if I add this bit, to my original delta, then and if I demand that this thing does not annihilate, then I can I can still have a decomposition of S, and that is what Anisha's question is. How is that working?
And I'm saying that, okay, let me rephrase it a little bit. So let's say I do this, okay, I define some new operator, which is given by the last equation that you written. J psi phi times delta half plus projector onto the kernel. This is the operator that you find.
Right.
This is in principle not S prime.
Hmm.
Okay. Now what you want to say is that if, let's say, J annihilates the projector,
Yes.
this is equal to Si.
Yes. Yes.
But now the delta tilde will no longer have a kernel, because that clearly that thing does not because this is projector thing, so the kernel
Right.
this does not have a kernel. So you're somehow transferring the kernel from the delta to the J. So you're
To
writing
i-
something new. And so whenever you have a kernel for S, it seems like the polar decomposition is not unique. That's how it.
Yes. Yes.
So you can always have a kernel on delta or a kernel on J.
Yes.
But then J need not be anti-unitary. That is the confusion.
Yeah. Yeah. I get the confusion. Even.
But where are you trying to go with this? Maybe we can guess.
Yeah. So. The units here. Sorry.
I said if J has a kernel, doesn't unitarily preserve information and things like that. Huh? And these are some complex conjugation. It is not analyzed. I mean, if I have only like a if all the coefficients are only real, then it's
One way to say it is J square is unitary. J is anti-unitary. And hence it can't have a kernel.
J square is, yeah. So I have to think a bit more. Maybe we can talk about this. Okay. So finally, I'm going to define. Oh, okay. Okay. I will just define this particular object and then we can break. Okay. We are going to define now relative entropy. This we define as associated to some space-time region U psi again psi continues to be cyclic and separating. This is the definition. So in general this is a real number and it can also be plus infinity, and precisely because it can have 0 eigenvalues it can go to plus infinity. And again some properties is that this object is always non-negative. U. I mean there is a space-time region associated with this. So
U is on sigma.
U is on sigma, yes. S psi phi is non-negative, and another thing that you see is where?
I mean, wasn't it the relative Tomita? I mean, just conflict of notation.
Oh, yeah, I guess we have to just go with it because entropy is also called S.
Make it curly or something.
Okay. Let me put it. Oh, this is what I will be using for. Is that fine? Okay. So this part is quite easy to see. So if this object, if phi is connected to psi using a unitary operator, what you can show is this is what happens. Now, if you recall, we also defined this. Okay. Now choose f of x to be log, and what you end up getting is precisely log delta
Why is that true? Delta psi, but alpha psi is the same as delta psi z. Sorry, delta psi a prime psi is the same as delta psi z.
Oh, that will essentially follow. Where is the? This will follow from the definition. Yeah. So you have if you simply put here this the S of. Sorry, hold on. Phi. Phi. Okay. It's going to follow from A psi is, just a moment, this should come out trivially. Okay.
Is that any unitary
I
part
think
should go
from the
into J
relative
alone?
modular operator definition,
Yeah.
if you put A prime psi term phi, and since A prime is commutant, A prime commutes with A.
Right. Yeah.
And
Exactly.
it will be proportional to
Yes.
delta psi psi, I guess.
Right. No, it should be exactly equal to delta psi psi, because if you plug in here phi equal to A prime psi.
Minus A is unitary, so A dagger A is 1. Okay, got it.
Yeah.
So from the from
I
here you
think
say
here.
times S psi phi, S psi psi.
Sorry.
From relative modular operator definition,
Yes.
S psi alpha
Yeah.
A prime psi
Hmm.
will basically be
A dagger A prime psi. Yes.
so now, and you take the A prime out, so S
Yes.
psi
Yes.
will just be S psi psi A prime multiplied that.
Yes.
And then you
Yes.
in the definition of your delta psi phi in S dagger S, the A dagger A prime dagger A prime.
Will give you one. Yes. Right. That is how this comes. Right.
I didn't follow, but
We can talk about. Yeah. So for the first part, in order to show this that this is non-negative, so we need to use a elementary identity, which is true for all non-negative real numbers, which we are just going to promote to operators, which is simply that if you have lambda greater than 0 and lambda belonging to our reals, then what we know is that log of lambda is less than equal to lambda minus 1. Okay. So when applied to operators, this is going to be simply delta psi phi greater than equal to 1 minus. Okay. Now if you simply sandwich between psi and psi, this is exactly, the left hand side is exactly what is S, which I have written as phi psi phi of u. So this must be greater than this entire thing, 1 minus delta psi phi on psi. Now the first part is just simply psi psi minus, here you have S dagger S. I am not writing the subscripts, it is phi psi, right? But we know that S acting on phi is nothing but, this thing is nothing but phi phi, right? You simply have to choose, go back to the definition, plug in here A equal to 1, and that's it. Okay, yeah, this is the last thing. So this is 0. So this object is always greater than equal to 0, non-negative. Okay. Okay. So the converse, by the way, also works. That is, so this inequality is saturated for lambda equal to 1, and if you do have this, so when lambda is equal to 1, you essentially need, you essentially have this equality. This boils down to this equality, and in terms of operator, this is what the statement is, and this essentially implies, and with some little computation, this implies this, and with a little bit of computation, what one can show is that this condition is effectively telling you and now observe that these objects A size or rather, in fact, this gets further generalized. I should. So these objects here, A psi and B psi, because psi was cyclic and separating, these are some dense. These are some dense kets and bras, right? Now, because of this particular equality, what we can say is that there is some densely defined operator that connects A phi to A psi, right? But that operator has to be unitary. So the statement is A phi is equal to some A prime A psi, where A prime belongs to the commutant, right? Because it also has to commute with my A's.
Could you repeat this part after 0 once more?
So
After you proved
after, yes, so I started with this, and this essential statement for two operators A and B, this after some bit of computation can give you this, right? Now psi is cyclic separating. So these things are densely, these are densely defined objects in some sense, right? So that means there must be some densely defined operator which will connect these states A phi to A psi and B phi to B psi. But that operator has to be unitary, right? Because in between sandwich will be that operator. Suppose that operator you call O. So O dagger O is sandwiched. That's why these two things are equal, right? And that is essentially what I have written here. So this A prime has to be unitary, which means, but A prime and A commutes, which means phi psi, A prime psi, where A prime is unitary. So this proof works the other way also. If you start with this condition, you will see that if you start with this, you will see that if this thing has to vanish, then
Did we prove for lambda equal to 1?
we prove that if S of psi phi u, if this is 0, then phi must be unitarily connected to psi. That is what we just proved. Okay? Okay. So I think this will be a good point to stop, and I will pick up by proving certain, Suchetan mentioned certain bounds, certain positivity conditions that are there in the context of relative entropy. So relative entropy has to follow certain basic bounds such as strong subadditivity. So these things come up generally in multipartite systems. We will try to derive those, how this entire structure gels in with that, and I will try to do two examples, one for a finite dimension and one for QFT, a simple QFT in 1 plus 1D, and how to get to the modular Hamiltonian. Yeah.
Is all the delta that you write down now, are they the original delta or this deformed delta?
What is the deformed delta?
I think this delta is positive definite or positive semi-definite? Does it have a kernel or not?
So this can have a kernel because this can have 0 eigenvalues. So this can be plus infinity. Yeah, this thing is either a real number or plus infinity.
So you haven't used any of that aspect anywhere?
No. I have not used this. I am not using this. Irrespective of this thing works. Okay? Yeah, sure.
In all these relative entropy computations, do you always need the modular operator and not this Tomita operator, Tomita operator?
No, you will not need the Tomita operator. You will actually be working more with the modular operator. And yeah, there is a reason for it actually. So in the context of finite dimensional systems, what you will see is that this modular Hamiltonian essentially can be written in terms of density matrices. So if you have a sort of purified system where you have taken two copies and you have written the most generic state. So you can always use singular value decomposition. You can start with the most generic this thing, tensor product state. You use singular value decomposition, you do this mid decomposition, and you can essentially write it in this form. So on this purified state, you can have partial traces now. You can either trace on K prime or this. So think of this as just some sort of a ancilla system that I have introduced to purify things. And what happens is that if rho 1 is the reduced density matrix of system associated with this one, the first system, and with the second system, what you will see is that you can show this. This is a very well defined object. You see, because, so just to give you a pictorial description, suppose if I would have given you a spin chain and you have made a copy out of it, so you had something like this. Now, now at each and every site you have this density matrix sitting, which is like this, half each of these sites, right? You have created some EPR pair like states. So with each of them you have, so that object is nothing but, now you take a tensor product again with the second one, what you will get is, you keep on doing that. You see what is happening. When you take n to be sufficiently large, each of these things diverge. And then you are going to take a trace of rho log rho, right? So you don't even have a well-defined reduced density matrix for the full system, for the n qubit system, if you want to call it. Whereas this object happens to be well-defined. In fact, in QFT, this has a very rigorous definition. In fact, in QFT, as I will mention later, that so the nice convergence, etc., I mean, well-definedness properties of this particular object actually follows from a limiting sequence of such matrix algebras. This is how actually it is done. I mean, this is the best proof of well-definedness and boundedness and etc. Not boundedness. The fact that this is well-defined and can be defined over the full Hilbert space can be derived from this. So this is the kind of motivation that should be there. So it need not be true that there has to be a density matrix for every system. You can have things like this.
Here, in this relative entropy, when you are taking the trace, there will not be multiplication of delta before this log.
Sorry?
Like this trace of rho log.
Oh, no. I'm not defining entanglement or relative entropy. So you will see, and I will do this. This will boil down to your standard definition of rho 1 log sigma 1 minus rho 1 log sigma, rho 1 log rho 1. It will boil down to that definition, at least for finite dimensions, finite dimensional quantum systems. I will demonstrate that.